All right, let's talk about RSA cryptography. You might not know the name, but it's the invisible shield protecting, well, pretty much everything you do online. Your emails, your bank details, all of it. And it's all built on solving a puzzle that seems completely impossible.
So think about it like this. How could you possibly get a secret message from someone in a crowded public square? I mean, a really crowded square, like the internet. You could give them a locked box, sure, but how do you give them the key to lock the box without someone else just snagging a copy of that key? It sounds impossible, right? Well, that's the exact problem public key cryptography was invented to solve.
You see, the old way of doing things was something called symmetric cryptography. Super simple idea. You have one key, it locks the box, and that same key unlocks the box. Kind of like your house key. Works perfectly, until you have to get that key to your friend across the crowded square. Big problem. But public key crypto, like RSA, pulls off this amazing trick. It creates two keys. One key just for locking, and a totally different special key that's the only thing that can unlock it. Game changer.
Okay, let's get into how this actually works. The core idea is just brilliant. You basically create a bunch of open padlocks. These are your public keys. You can just throw them out into the world, leave them on a park bench, doesn't matter. Anyone, and I mean anyone, can pick one up and snap it shut on a box to send you a message. But here's the magic. You, and only you, have the one special key that can open that padlock.
So what's the secret sauce that makes this possible? It's a concept called a mathematical trapdoor. And it's exactly what it sounds like, a function that's super easy to go through one way, but unbelievably hard to reverse. Imagine mixing two colors of paint. Easy, right? Now, try to unmix them. Get those two exact original colors back out. Yeah, good luck with that. That's the basic principle RSA is built on.
Okay, so to build this mathematical trapdoor, we're going to need 4 key ingredients. And hey, don't worry, we're not about to dive into a super heavy math class. Just think of this as the recipe for our digital padlock.
Ingredient 1, prime numbers. You probably remember these from math class. Numbers you can only divide by 1 in themselves. But here's the thing that matters for us. Multiplying two absolutely gigantic prime numbers together, a computer can do that on a flash. But if I just give you that enormous final number and ask you to find the 2 original primes I started with, whoa, that is an insanely hard problem. And that difficulty, right there, is the bedrock of RSA security.
Second, we've got something called modular arithmetic. Sounds fancy, but it's really just clock math. You know, if it's 10 o'clock and you wait 5 hours, it's 3 o'clock, not 15. The numbers wrap around. All this does is keep the massive numbers we're crunching in a nice, neat, predictable range. It keeps things from getting out of control. Third ingredient is called Euler's Totient function. Look, all you really need to know about this one is that it's a special little function that we plug our 2 prime numbers into. It spits out a kind of magic number that's absolutely critical for making the public and private keys talk to each other. It's a key piece of the engine.
And our final ingredient, the modular inverse. This is the step where we actually forge the 2 keys. We basically choose a number for our public key, we'll call it E, and then we use this cool mathematical relationship to calculate its partner, D. And that D becomes the heart of our private key. They're 2 different numbers, but they're now mathematically connected forever.
All right, we've got all our ingredients. Let's actually put them together and make a set of keys from scratch. Okay, step 1, pick 2 prime numbers. We'll use tiny ones just to make it easy. Say 61 and 53. Step 2, multiply them together. That gives us our n, which is 3,233. Step 3, use that Euler's Totient thingy on our original primes. That gives us 3120. Step 4, we pick a public number, e. Let's just go with 17. And finally, step 5, we do the math to find its modular inverse, d. And poof, we get 2753. And just like that, we have our key pair. The public key is made up of our E and N, so that's 17, 32, 33. You can post this on a billboard, tell everyone you know, it doesn't matter. But the private key, that's our D and N, 27, 53, 32, 33. This one you guard with your life, it's your secret. So we've got the keys, now what? Let's see the magic happen. We're going to take a message, lock it up tight using only the public key, the one everyone knows about, and see if our private key can really set it free.
Let's say our secret message is just the number 65. Now, in the real world, your whole email or photo gets turned into a giant number, but for this, 65 works just fine.
Okay, time to encrypt. The formula is pretty straightforward. We take our message, 65, and raise it to the power of e from the public key. So that's 17. Then we do that clock math, the modulo, using n, which was 3233.
The computer crunches those numbers and out comes 2790. This is our encrypted message, our ciphertext. I mean, look at it. It looks like total gibberish. You'd never in a million years guess it started as 65. It's locked up tight.
All right, this is the moment of truth. To get our message back, we use a similar formula, but this time we bring in the secret weapon. We take the scrambled number, 2790, and raise it to the power of our private number d, that's 2753, and then do the same clock math with n.
And would you look at that? After all that math, we get 65. Back to the original. It works. The public key locked it, and the private key unlocked it. That is the absolute genius of RSA. And this little mathematical dance, it happens in the blink of an eye every single time you see that padlock symbol in your web browser. It's what keeps your secrets safe online.
So it feels like magic, but is it unbreakable? How secure is this really? Well, its strength isn't magic at all. It's based on a really hard math problem. Let's talk about what it would actually take to crack it.
Okay, so the security of this whole thing hangs on one simple fact. An attacker can see your public key, right? So they know your number n. In our little example, that was 3233. To break the code and find your secret key d, they have to figure out the two original prime numbers that you multiplied to get n. And like we said, with the giant numbers used in real life, that is a monstrously difficult task for any normal computer.
Now, it's not foolproof. You can mess it up. If you use primes that are too small or make other dumb mistakes, it can be broken. But the real threat, the thing that keeps cryptographers up at night, is something else entirely: quantum computers. There's a thing called Shor's algorithm that, if run on a powerful enough quantum computer, could solve that hard factoring problem like it was simple addition. And if that happens, RSA as we know it is basically toast.
But for today, for right now, RSA is it's a masterpiece. It's one of the most beautiful examples of how super abstract, pure mathematics can be turned into something so practical and so vital for our digital lives. It's literally the foundation of online trust.
And that really leaves us with a huge question. With these quantum computers looming, there is a global race happening right now to find the next kind of public lock, a new kind of mathematical trapdoor that even a quantum computer can't pick. So the question isn't really if RSA will be replaced, but rather what amazing new idea is going to replace it.